So the wonderful thing about physics is that every time you answer one question, another question almost automatically suggests itself. In the last recording, the last lecture, I discussed, and you got to think about, what happens to a solid when its temperature changes. And the answer turned out to be that its dimensions changed. Length, area, volume, depending on whether those dimensions were comparable to each other or not. And so we said, okay, if you raise the temperature of a piece of steel or a piece of glass or a piece of aluminum by 1 Kelvin, its dimensions change by this much. And it was determined in part by, and how much the dimensions changed was determined in part by a property of the material called the coefficient of thermal expansion or contraction. Okay, that's the alpha. And then I hinted briefly at liquids behave somewhat similarly. And that then suggests another question automatically, perhaps, and that is, how do you get an object's temperature to increase or decrease by 1 Kelvin? What do you have to do? In fact, well, and so that's one question. And so the answer to that question is, of course, you have to do work on it somehow, or you have to have some heat flow into it, have some energy get transferred into it by some mechanism or other. I am not going to, in this recording, concern myself with how that energy gets into the system, how the heat happens. Let's just suffice to say that, or let's confine our attention, I guess I should say, to the question of how much energy, how much work, how much heat we have to transfer into or take out of the system in order to change its temperature. Okay, so the fundamental question is, how much energy does it take to change the temperature of an object? Okay, and once again, as was before, and it's been true so many times, hopefully it's reasonable to think that the amount of energy it takes to change the temperature of an object depends at least partly on what that object is made out of. Okay, and that is true. Another thing that, well, let me write down the question. All right. Now, technically speaking, the answer to this question should include both heat in the form of, represented by the letter Q, and as well as work done on the system or work done by the system in the form of W, right? And you'll recall the first law of thermodynamics, that the total change of the thermal energy of a system is equal to the sum of the work that you do or on the system, or that the work does, or the work that the system does, and also how much heat flows out of the system. Okay. However, it turns out in practice that by far and away the biggest contributors to temperature change turn out to be the heat flow, and the work done on a system is often small compared to that. So let's focus our attention on just answering the question, how much heat do you have to either add to or take away from a system in order to increase or decrease the temperature of that system? Okay. By the way, since we're talking about adding and subtracting heat, evidently we have at a minimum a closed system, certainly not an isolated system. Probably closed, probably not open. We're going to let the mass remain constant. In fact, let me be definite on that. We have a closed system, so the mass of the system cannot change, but the energy content can. All right. So I'll toss that in, a closed system. Okay, so we've already said one thing that is going to matter is going to be what the system is made out of. If it's made out of water, if it's made out of gold, if it's made out of wood, if it's made out of carpeting, the answers are going to be different here, okay? So let's see. the nature of the material, what the system is made out of. Okay. And second of all, how much energy do you have to add or subtract from a system to change its temperature? Well, doesn't seem reasonable. It depends on how much mass you have, how big the object is in terms of mass. If I want to raise the temperature of a tiny little fragment of steel, like let's say a sewing needle or a push pin or something, it's very small, and it doesn't take much heat at all to significantly raise the temperature of a little tiny push pin, right? But if I got a chunk of steel that was 400 kilograms, big block of steel, it's also steel, just like the pin is, but I hope you'll agree that it's going to take a lot more heat to raise the temperature of a great big honking block of steel than it is just a little tiny sewing needle. Even though they're both steel, it's going to take more heat for the more mass. So that seems plausible. Okay. And finally, how much do you want to change its temperature? How much do you want to raise its temperature? How much do you want to lower its temperature? Okay. The more you want to change its temperature, the more heat you've got to add or subtract depending on the direction you're going. Okay. So let me actually write that temperature change. Okay, and so as we always do, we'll give these things symbols. The temperature change, I've already sort of given that one away, and you already knew it anyway. We'll call that delta T. Mass, obviously, we'll call that M. I don't know, capital M, lowercase m, doesn't matter. And then the nature of the material, I will represent this with the letter C, lowercase c. Okay? Lowercase c here has a name, which is a rather peculiar name I've never quite understood. I sort of understand why it has this name. It's not the most obvious name in the world, but whatever. C is called the specific heat. Which, as names go, is a pretty terrible name because first off, it isn't heat. Okay, it's related to heat in some way, but C is not heat. Okay, the word specific here refers to the fact that this is a property of a kind of material, rather than a property of a specific object made of that material. Okay, so to use the analogy that I did a moment ago, a little tiny sewing needle and a huge block of steel they both have the same specific heat, the same value of C, even though they're obviously quite different in terms of mass. Okay, so I would love to call C something, almost anything else other than specific heat, but that's the name it has, and we're just stuck with it, I'm afraid. The specific heat its use is exactly what we're doing here. So it tells you how many joules is required by either adding joules or taking away joules of energy. One kilogram of a substance by 1 Kelvin. So a given material, again, different materials will have different physical properties, and one of the consequences of the different physical properties will be how much energy do you have to add or subtract from this particular material, from steel, from aluminum, from water, from cotton, in order to change its temperature, in order to change 1 kilogram of your substance by 1 Kelvin temperature. Okay. calculation then becomes the amount of heat, Q, required to accomplish this is calculated simply by multiplying the mass, well, I'm going to write it the way it should be written, and then I'll write it the way everybody actually does write it. Multiply the specific heat times the mass of your object multiplied by the temperature change that you want. For mysterious reasons, at least mysterious to me anyway, this is typically always written m times c times delta T in that order. I always like to put the proportionality constants out front, but that's not what's done here. Thermodynamics is a very odd science. Anyway, there's the calculation, okay? And not terribly difficult, and there's a high probability that you've seen this before anyway. So let me go ahead and do an example in this recording rather than doing a separate one. Sorry, I'm rolling the camera around here. I'm trying to get off of an electrical cable here. Okay, so let's see real quick. Let's go ahead and do a common, familiar household example that you've doubtless done many times. Let's suppose you have 1 kilogram of gold. It's placed inside a pot of water, also 1.5 kilograms of water. Sorry, let's say a pot that holds. And the water and the gold are both at 0 degrees Celsius. That's 273.15 Kelvin. But they're just above the freezing point of water, so that the water is liquid, but at 273.15 Kelvin. All right, and then we turn on the fire, turn on the stove. And let's boil the water with the gold still in it. And the boiling temperature of water is 373.15 Kelvin. The question that we're going to ask is how much energy did the water get? And how much the gold? I will leave it as a separate problem to determine the volumes of the water and of the piece of gold here. Okay, it's not relevant in this problem, so I'm not going to do it. But I think you might want to. It might be a good idea if you did it on your own. Okay. Anyway, let's see. So what do we have? We have. So we'll draw a diagram. Pot of water. A little chunk of gold in it. Let's see, what color pen do I have that's closest to gold? I guess that's gold. Okay, so that's our gold. Yes. And then Surrounding it is water. And in case you couldn't tell, this is supposed to be, I guess, the handle of the pot. And by the way, this is actually relevant here. Why do pots have handles? Because the handles are typically made of plastic or some other material that has a very high specific heat, and so it can absorb a lot of heat without its temperature changing very much. Okay. All right. So let's have a look at this. So the heat for the water is going to be the mass of the water times the specific heat of water times the change of temperature, which is going to be the same for both of them. Okay, so there's that. And so we plug in the numbers, and I have to look this up in a table somewhere, and I find that, well, I'm sorry, the mass of the water is 1.5 kilograms. I artificially had both the mass of the water and the mass of the gold be the same because I wanted to compare them, of course. The specific heat for water is 4,157 joules per kilogram of water per Kelvin that you want to raise the temperature. And the number of degrees, the number of kelvins, I'm sorry, that we want to change the temperature is 100 Kelvin. Okay? This is how much we want the temperature to change. We want to go from 273.15 Kelvin to 373.15 Kelvin. So a change of 100 Kelvin. Okay? And I plug in that number, and I got 623,550 joules. Okay? Meanwhile, for the gold, exactly the same kind of calculation, the mass of the gold. Remember the chemical symbol for gold is Au, okay? Times the specific heat of gold, times the same delta T, mass, again, just so we can compare them, 1.5 kilograms of gold, specific heat of gold, again, I looked that up, and that turns out to be just 129.1 joules to raise 1 kilogram of gold by 1 Kelvin. And then again, increase it by 100 Kelvin, and I work out that number, and that turned out to be 19,365 joules. Okay, and you'll notice that the amount of heat that it took to increase the temperature of the gold was a lot less than the amount of energy it took to heat the water up that same amount. And indeed, you might suspect, and you'd be exactly correct, that the ratio is 4157 over 129. So, a factor of roughly 35 or 40 times as much heat for water as for gold. What this tells you is not that gold is particularly easy to change its temperature. It's actually fairly typical. No, what's unusual is how much heat is required to change the temperature of water. Water is highly unusual in this particular property. It takes a lot more energy to heat up water, and therefore it takes equivalently takes a lot of loss of energy before you drop the temperature of water by one Kelvin, compared to other substances. Another, to say that a little more clearly, water becomes the temperature of water drops only very slowly, very reluctantly, and with a great deal of difficulty. You have to drop a lot of energy. You have to drop over 4,000 joules of energy just to decrease the temperature of water of 1 kilogram of water by 1 Kelvin. It's a lot of energy compared to how much energy gold would have to lose to drop its temperature, right? And the consequence of that is that water stays liquid over a much larger range of temperatures than almost any other substance on Earth. Okay, it stays liquid over a range of 100 degrees. I'm sorry, 100 Kelvin. And there's no other substance on Earth that comes anywhere close to that in its liquid phase. Okay, and it is for that that is one of several reasons why water is the single most essential molecule for life. Simply because for life to, well, there's a lot of reasons, but one of them is for life to even happen. Life represents a very complex interchange and movement of chemicals from here to there, right? Chemicals are constantly moving in and out of your cells, throughout your bloodstream, back and forth, all sorts of transfers of chemicals, all done under against a watery background. But that can't happen if the water freezes and you have ice and you don't have any movement of chemicals, and then and that's why animals die when they freeze. Okay, it's because all the chemical processes that make up life simply stop as soon as the water stops being liquid. But water stays liquid over an enormous range of temperatures because it takes an enormous amount of energy to change liquid water into solid water or into gaseous water. Okay, and so water is a very, very good chemical to be the basis for life. And that's one of the reasons that when astronomers go looking at planets outside of our solar systems, one of the first things they look for is the spectral signature of water in the atmosphere. Because if there's no water, there's no life, or at least no life as we know it. So that's that. Okay, so that's specific heat. And there are other properties of solids that have to do with temperature, and we'll talk about those. And in fact, let's think about what I just hinted at, is that materials such as water, but not just water, what happens in the process of converting from liquid to a solid or from a liquid to a gas? How does that work? How do those phase transitions work? They're related to temperature also. We'll tackle those next.